Consider the field extension K of F. F is a subfield of K. K is an extension of F. And consider a subset S of K. The smallest subfield of K. The smallest subfield of K containing both F and S. It is denoted by F of S. Okay, the smallest subfield of K containing both F and S is denoted by F of S. Definitely such a field exists. Why? What is this? It is nothing but the intersection of all subfields of K which contain both F and S. Okay, this subfield F of S, it is called as the field generated by S over the field F. Okay. Now, if I consider the set as having the elements alpha 1, alpha 2 and so on, alpha n for instance, okay, then we write F of S. Okay, it is nothing but we will write it as F of alpha 1, alpha 2 and so on, alpha n, the field generated by these elements over the field F here. Okay, so and it is the smallest subfield of K containing F and the elements alpha 1, alpha 2 and alpha n. Now if this subset S of K, if it has only one element, say alpha, okay, then what is this F of S? It is F of the singleton set alpha, right? So it's denoted by F of alpha, and this is the smallest field containing the field F and the element alpha. Okay, and this field F of alpha, it is called as simple field. So an extension K by F is called simple extension. It is called as simple extension if this K is generated by the single element say alpha belonging to K over the field F. Okay, so we say that it is a simple extension if I have K is equal to F of alpha, and this element alpha, it is called as the primitive element for this extension. It is the primitive element for the field extension K of F. Okay, and the K is obtained from the field F by adjoining the element alpha. This extension is obtained from this field F by adjoining the element alpha here. Okay, so the size or we call it as the degree of F of alpha. Okay, degree of F of alpha over the field F, it depends upon whether this alpha is a root of any polynomial or over F or not. Okay, so degree of F of alpha over a field F, it depends upon if alpha is a root of a polynomial over F or not. F of alpha is the extension of the field F, right? So what we have here, F is contained in F of alpha. What is this? It's a ring. Okay, ring generated by the element alpha and the field F. So this is contained in the field F of alpha, where this represents the field generated by alpha and F. Note down the difference between these symbols here. F in the bracket alpha, it is the ring generated by alpha and F in the parenthesis alpha, it is the field generated by alpha and F. Okay, so what are the elements of this ring? It is the A0 plus A1 alpha and so on, AN alpha power n, where each AI are elements of F and n is a positive integer. So I can write this as equal to F of alpha, where F of x belongs to F of x, the ring. And what are the elements of this? What is this actually? It is the field of quotients of this ring F of alpha. Okay, so what are its elements? They are of the form, say A0 plus A1 alpha and so on, a m alpha power m divided by say b naught plus b1 alpha and so on, b n alpha power n. Okay, an element of the ring f of alpha, an element of the ring of f of alpha. Okay, such that each coefficients ai's and bj's are from f, and the powers n and m are positive. And if you consider the GCD of the coefficients of in the denominator, say b naught, b1 and so on, bn should be non-zero. Okay, so in other words, I can write it as, if I consider this as f of alpha, this as g of alpha, then I have f of alpha by g alpha or g of alpha, where f and g are polynomials over f, where g is non-zero polynomial.